All right, thank you, and thank you, Livu. Let's see. Is it loud enough? Okay. I teach calculus in big rooms, so I think I could probably do it without, but don't want to make people go deaf, you know. So I'm here to entertain you. You've had classes all day, and then for too long during the semester, you know. So I'm from Duke. I don't like their basketball team either, so you don't have to worry about that. All right, so sort of an ostentatious title. One of the things about probability is there are lots of, you know, interesting examples, some things that look sort of a little strange to the eye and don't turn out to be that strange. So we're going to walk you through some of these things, beginning with one of the, simplest problems, you know. So how many people have heard of the Monty Hall problem? Well, that's good. Okay, so you understand this, so now I'm going to confuse you, you know. So this is from a time long ago when I was small, and what was being outrageous is dressing up like Raggedy Ann to get on a game show, and that, of course, is Monty Hall right there, you know. So what's the situation? There are 3 doors. Of course, on the TV show, you have 3 big curtains, and you know, Vanna White or whoever was walking around in some evening gown, but you know, you have to deal with me instead, you know. So, and in this idealization, there's a car behind one of the 3 doors, and what Monty did was to build the suspense, and hopefully to make you look foolish, he would open one of the doors. All right, and we need to, you know, so there's a car and 2 goats. So he would open the car and open the door and show you a goat. All right. So now the question is, should you switch? You know, you had door number 1. Should you switch? You get an opportunity to switch to door number 2, and should you do it? All right. And so let me tell you a little story. Marilyn Vos Savant, that's sort of an interesting name, is an American magazine columnist, author, lecturer, and playwright who rose to fame through her listing in the Guinness Book of World Records under highest IQ. She had her IQ tested when she was 10, and she scored like a 21-year-old. So this gives her 210. Actually, they're supposed to truncate the score at 150, but who knows. So since 1986, she's written Ask Marilyn, a Sunday column in Parade magazine. So here we are. The smartest woman in America, what does she do? She writes a column for Parade magazine, all right? All right, so it'd probably be worse if she was president, who knows? All right, so she wrote her column, you know, some of this is older, maybe, not quite before you were born, and she talked about the Monty Hall problem. And she answered arguing that the selection should switch because that gives you a 2/3 chance of success. And there followed a bunch of funny letters about this. And this is one that I really enjoy, you know. So, yeah, I'm sorry, I'm going to read some of the slides to you. You just take a nap, you know. So, you blew it, and you blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. That's in red because you'll see this guy never explains anything. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There's enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame. Scott Smith, PhD, University of Florida. I'm glad it wasn't Notre Dame here, but anyway. So, okay, let's do some math. Calm me down here. So there are 3 places the car can be. Behind door 3, door 2, or door 1. So after you pick number 1, you know, if you have case 1, the car's in number 3, the host is going to open door number 2. If it's case 2, the car's in door number 2, the host is going to open number 3. If it's case 3, it's car's behind door number 1, host can do either one, right? So since he opened door 3, we know case 1 is off the table. So I'm going to compute some probabilities, so ask somebody that's in his class if you're confused, but so in case 2, he always opens door number 3. So being in case 2 and opening door number 3 is a third. Now, being in case 3 and opening door number 3, that's you have to be in case 3, that's a third, and then he has to choose one of the 2 doors. So that's only 1/6. You add those 2 probabilities, and you have the surprising fact that the probability opens door 3 is a half, right? So there are 2 doors left. They should each have probability half. But now if we look at the conditional probability, that's case 3, given door number 3 was opened, well, case 3 and door number 3 is opened as 1/6 divided by a half. So the conditional probability is a third, all right? So that's boring enough to be a calculation, so. A much simpler thing is that before he opened the door, your chance of winning was a third. And he can always open the door and show you a goat. So doing that hadn't changed your odds. It's still a third. So this brings me to another letter. This guy's, do you mean to tell me if there are 100 doors and I pick one and the host opens 98 doors, that now if I switch, I have a 99% chance of winning? Yeah, I mean exactly that, but, oh, whoops. Uh-oh. Don't edit your slides 30 minutes before the talk, so I have a 98 something or other, all right, so. There will be typos in the lecture, so. So the Monty Hall problem comes up in lots of disguises. So this one, you probably read a lot about cognitive dissonance and monkeys, so. Yale psychologists measured monkeys' preferences by observing how quickly each monkey sought out different colors of M&Ms. It makes me happy I'm a mathematician, so. So I can imagine these guys in tweed jackets walking around dealing with monkeys. Actually, I'm lying. They're graduate students are walking around, whatever graduate students wear, dealing with the monkeys, So in the first step, the researcher gave a monkey a choice between, say, red M&M and a green M&M. And then if it picked the red, it left the green there and put out a blue. And nearly 2/3 of the time, the monkey rejected green in favor of blue, which seemed to jibe with the theory of choice rationalization. Once we reject something, we tell ourselves we never liked it anyway, all right? So I don't know if this applies to ex-boyfriends, so I was a nerd. I didn't get out very much when I was growing up, so. All right, so it's pretty heavy for a monkey, so it's choice rationalization, so. All right, well, if you got a monkey, and monkeys are pretty random, they have 6 possible orderings between the 3 colors of M&Ms, all right? In 3 of these orderings, red is preferred to green. And cleverly enough, those are ones in red. Let's look so once we know they prefer red to green, our sample space, I'm supposed to throw some jargon out, right, had 6 points, but now it has 3. And we look in these 3 points, and 2/3 of the time, blue is better than green. So the monkeys aren't doing choice rationalization. Did I score a touchdown, or is this what? Is this a touchdown Jesus move, or okay? All right. Well, that's good. He's a math professor. He has a low threshold for excitement, so. I'm not coming back here anytime soon, so. All right, so birthday problem, it's like probability greatest hits. Somebody wants to bet you $20 that in a group of 40 people, for example, the Boston Red Sox roster of active players, since I don't have 40 friends to go out and bug, no 2 have the same birthday. Well, a little fact about life, if somebody comes up to you and wants to bet you something that sounds like you're going to win, you're probably not, all right? So All right, so actually 40 is way off the mark here. So if you have 40 people, it doesn't sound much like you got this calendar with 365 days. And I'm going to throw 40 balls at the calendar, and these represent the people. So it sounds like 40 is much smaller than 365. So why would you hit the same thing twice? Well, there 40 times 39 over 2, or 780 pairs of players, of people. People, players, whatever. Oh, players on the Boston Red Sox. And they each share a birthday with probably 1 over 365. So now I have 780, not independent, chances of getting an event or probability 1 over 365. So your little friend's going to win the bet 89% of the time. And, not to leave you, you see, I gave them this talk a few times. So once in my old alma mater of Emory University. So, Atlanta Braves 2014 roster, their 2 birthday coincidences. All right. And it's not hard. You probably did this in your class, right? So this is the formula. It's not really a math talk without formulas. And this is a graph. So at about 22 is sort of the break-even point. I taught at UCLA for a while. And a friend of mine, a statistician, did the birthday problem in a class of size 50 and didn't get a match. They were probably just screwing around with him, but all right, so. All right, so let's, kick it up a notch, You're sitting here watching TV, and it's like, are there 3 senators with the same birthday, So that's what mathematicians do when we watch TV. Actually not, So this was a problem in my class, so. So I'm going to calculate the probability of a group of 100 people, there's at least 1 triple birthday. This one's not easy. You might give that for extra credit or something like that, but. All right, so we're going to take it a different way out. If I look at 1 birthday, there are 100 people that have probability 1 over 365 of having that as their birthday. Now, when I'm in a situation where there are a large number of trials and small probability of success, then success has approximately a Poisson distribution. I'm not going to define that. You're going to have to go, if you hadn't already had a course, go take one. So Poisson, I have to write one formula. Poisson would mean lambda, the probability is equal to k, is lambda to the k over k factorial. So it's a lot easier than messing around with the binomial thing. So probability of 3 people on 1 given birthday is like 2.6 times 10 to the minus 3, but then there are 365 birthdays, so that on the average we'll have 1 triple birthday in a group of 100 people. Double birthdays are more common, so in a group of 100 people, there should be about 10.4. Now, I don't know. I was bored when I was preparing for this talk. Go on Wikipedia, look at senators sorted by their age, and then you list the months and list the days. What else do I do while I'm watching TV? There's 1 triple birthday. Sorry, didn't involve anybody from Indiana. And there are 10 birthdays. So it's almost exactly what you predict. And it's this year, so I didn't fudge it, so. And I don't know, the double birthdays are not so exciting. Dianne Feinstein and Elizabeth Warren were born on June 22nd. What does that mean? Nothing. It means nothing. So Paul Ryan and some guy I never heard of were born on the same day. That didn't seem like such a great example. All right, so Chad and Barbara Soper will have an easy time remembering their kid's birthday. So one was born on 8/8/08, another one on 9/9/09, one on 10/10/10. So what probabilists do is walk around, asking what's the probability of this. And Philip Stark from Berkeley says, well, depends on what you assume. You know, if you picked these days at random from the calendar, it's like 1 over 365 cubed, all right? But let's get into a little biology, you know. So from the first kid being born to the second kid being born is 13 months, which is good because you need sort of 9 months in between, you know. So I don't know about this couple, but, you know, right after my kid came home from the hospital, I was too tired to be amorous, you know. But that's me, you know. So you got to say energy to do math, you know, so whatever. So I have no idea. This guy says 1 in 2,500. I don't know. So now there are always facts that you don't know. Labor was induced for the third child. So were these people cheating? No. The woman, labor was induced on 10/9/10. So I don't know. So the woman sat there more than a day in labor, you know. So. But now she's famous, you know. She's in this talk, you know, so. All right. So yes, they do let me out just for short stretches of time. All right, so let's do, you know, the math literacy in this country is remarkably low. So this was a real story in the paper, you know, so. Lottery officials say that there's a 1 chance in 100 million that the same 4-digit lottery number would be drawn in Massachusetts and New York on the same night. That's just what happened on Tuesday. The number 8902 came up paying some amount in Massachusetts, another amount in New York. So anybody want to tell me what's wrong with this? Or what the right probability should be? What's wrong with this? This is the probability that both states picked 8902. I think I would be equally surprised if they both picked 5573, but that's just me, you know. So Massachusetts is going to pick some number, right? And then New York has to match it with probability 10 to the minus 4, all right? So.
It's also the case that there are lots of pairs of states, not just Massachusetts and New York. So if I
yeah, okay, that's good. So it's another thing that makes it even more likely. That'll come up in the next example too. So, all right. But yeah, I mean, you know, there are lots of lottery. There's one of these lottery drawings every day. There are lots of pairs of states, you know. So, all right. So it's sort of a sadder one here. Sally Clark. A British jury convicted Sally Clark of murdering her 2 children, who had died suddenly at the ages of 11 and 8 weeks of sudden infant death syndrome, that's what we call it in the U.S., or cot deaths in the U.K. So there's no physical evidence of murder, nor was there a motive. But they got somebody in there to tell the jury, well, 1 out of 8,500 children cot death. And she had 2. So the probability this happens by random chance is 1 over 73 million. And they sent her to jail for that, you know, and then there were a bunch of probabilists in England that lobbied to her defense and finally got her out. Well, what's the thing? The first one is free. I have no idea how many people there are in England, but they're probably more than 8,500, you know, so there are going to be a lot of people who experience cot deaths. So the first one is not really surprising. You just happen to be one of the unlucky few. And now this is a thing with a genetic component. So if you condition on having 1 child with this, you have a 1 in 100 chance that the second child has this. So instead of, you know, they were close. 1 over 73 million, 1 over 100, you know, so they eventually let her out, you know, so she spent 3 years in jail before the conviction was overturned. And the end of the story is not so happy, you know, so you lose both kids and you go to jail for 3 years, so, well, she died mysteriously of alcohol poisoning, you know, so yeah, like I said, maybe I shouldn't. Well, I did that thing in class, and one of my students says, "That's the saddest story I've ever heard." but I should probably leave off the last part. So let's go back. We're talking about people winning money here. So a New Jersey woman, Evelyn Adams, won the lottery twice within a span of 4 months, raking in a total of $5.4 million. And like most lottery winners, 6 months later, she was probably bankrupt because you win the lottery, suddenly you have a lot of friends who have lots of investment opportunities for you. All right, so they made the math really icky for us. The first time was a lotto. You have to pick 6 right out of 39. The second time is 6 out of 42. So the formula is, this little C in M guy is the number of ways of picking M things out of N. So once you do all the math, it's like, one chance in 17 times 10 to the 12th. I'm pretty sure I'm going to own the Notre Dame record for biggest numbers in a math talk here. So, but all right. So it's like this could never happen, in all of eternity, So, well, again, that's this is the part of the talk where the first one is free. Somebody won the October 23rd, 1985 lottery. So we ditched the first factor. Now, she won on October 23rd and February 13th. But, what the heck? If she won twice in a 6-month period or even a 1-year period, we'd be equally excited by that. So that's another factor of 100. Now, how many of you go out and buy lottery tickets every week? That's what I thought. There's some people that buy a lot of lottery tickets, So I remember seeing a guy who won on TV, borrowed $200 from his mother to buy 40 lottery tickets. You don't see all the other people who did that and lost all their money. So if you take into account the heterogeneity that a lot of people are buying, a small number of people buying a lot of lottery tickets is not really unusual. And as the man in the back said, well, there are lots of states that have lotteries, so, All right. So you may think I'm not impressed with anything. There's a story of Maureen Wilcox. She bought, this is Massachusetts and Rhode Island this time. She bought tickets for both the Massachusetts lottery and the Rhode Island lottery. Fortunately, the states are really close to each other. She picked the winning numbers for both lotteries. Yippee! Her Massachusetts numbers won in Rhode Island, and her Rhode Island numbers won in Massachusetts. So that's like really bad luck, So, but all right. So now that's unusual. Okay, lottery double winners, triple winners. We're going to get up to 57-time winners, So 81-year-old Keith Sellex won 3 lottery prizes totaling $81,000 during 12 months preceding May 3rd, 2006. He won $30,000 twice and $21,000 twice. And these games, it's typical lottery. You win $21,000, but the odds against you winning are 90,000 to 1. All right, so you should just go up and give them 80 cents and be done with it. So one of the reasons why Selleck won so many times, he spent $200 a week on lottery tickets. So it's like, this is what happens when your wife's not around to tell you not to do stupid things, So, but sorry, that's sort of a joke for old people, So, but let's do things round. 1 in 100,000 is the winning probability. He played like 10,000 times. So he had a 0.1 chance of winning once. Now, again, this is large N, small p. So the probability of winning 3 times is roughly Poisson with mean 0.1. And this is less than 1 over 60,000. All right. So he was sort of lucky. He paid in $10,000. He got out $80,000. but he won $80,000 with probably won over $60,000. Now let's have a little human interest story. This is the luckiest gas station in America. It's in Bishop, Texas. I have no idea how long a drive it is from here, so looks like a really romantic place, so. All right, so there's a woman, Joan Ginther, 63. She's won $21 million playing the lottery, right? And Associated Press, I don't know. Her chances doing this are 1 in 18 septillion. I didn't even know what a septillion is, and I'm taking their word for it, so. All right. So Joan got her PhD in statistics from Stanford. An article in Harper's Magazine suggested that she may have figured out the random number generator that makes the tickets. Like, yeah, right. And what's she going to do with that? Ginther lives in Las Vegas. It's a romantic place to, live, so. But spends 2 months a year in Bishop, Texas, playing scratch-off tickets. So that's, you're sitting there in a cheap motel in Bishop, Texas, with your little quarter, scratching these things off 8 hours a day, I'd rather teach freshman calculus, whatever. Well, the Lucky store was shut down by the IRS because it turns out that they tried to inspire the store owners by saying, oh, in this box of tickets, there's a winner. And when the store owner got that message, she put this box aside for Joan. So, that they got shut down, So, if I had $21 million, I'd do something other than spend 2 months a year in Bishop, Texas playing scratch-off. But, it's just me, so. All right, so sometimes there are too many winners. So Powerball officials were amazed, one time when 110 people won second prize in the lottery. This was in New Jersey, so they were suspecting maybe something was happening here. So based on the number of tickets, there should only have been an average of 4 winners, right? And this is the Poisson process. I hope you did the Poisson. It's the start. E to the minus 4, 4 to the 110, over 110 factorial. I typed that into my calculator. What you get back is 0, not even scientific notation. If you play around with Stirling's formula, it's about 10 to the minus 110. That's about the smallest probability we're going to see today. So what happened? Well, first clue is that all 110 winners played the same 6 numbers. The first 5 were in the sample, and they all had the 4th number wrong. Fortunately for the lottery, they didn't get the 4th number right because you'd have, 110 people with the first prize rather than the second prize. Actually, if 110 people win the lottery, including the Powerball, that's not so bad because 110 people split the overall prize. But these prizes are paid on sort of per basis. So how did this happen? The numbers came from fortune cookies from the same factory in Long Island, Queens. You've probably gone out and eat Chinese food. There's inside the fortune cookie, there's this little fortune. You put it on the other side. Your lucky numbers are this. Well, these people are cheap. They didn't want to have a random number generator in their computer, so they just printed the same numbers on all the tickets, So, and it worked, So, but strange things happen on one of the episodes of Lost, which probably aired before you were born, So, they had lottery numbers, and the next day, a ton of people went out and played those lottery numbers, So, to heck with that, get your fortune cookie and then go play based on that, So. All right, so, we're gonna be done before the pizza's here, but anyway, so. So some people are too lucky. In a Florida Play 4 game, you pick a 4-digit number, and since they think people can't count, if all 4 digits match an event of 1 over 10,000, they give you $5,000. It's like, okay. You know, it's like, here's 50 cents, you know. So some people are very good at winning this gamble. There are some people that, well, here's our friend Philip Stark from Berkeley, Richard Roches at USC, and these other two guys I don't know. There's some guy who we'll call LJ because we don't want to get sued, has won 57 times. Well, that's not, you know, by itself, that's not a proof of guilt. If he actually bought 570,000 lottery tickets, he could have done that, you know. But if he only bought 250,000 tickets, the probability he would win 57 times is very small. So what did he do? All right. So there are three different schemes. I learned this after I gave the talk at Emory. I mean, so you can take the little lottery scratch-off thing, and if you make a slight mark across it with a pen, it takes some of the gray stuff off. You don't need to do too much of that, so you can actually scan the barcode underneath and see if it's a winner. Or you can just straight out cheat people. Sometimes people will come in, they're too lazy to look at the newspaper. They're like, is this a winner? The clerk goes, no way. I'll kind of keep the ticket in my pocket, you know, so, and they keep the money, all right? Sometimes if you win and you're an illegal immigrant, owe child support or back taxes, then if you can't get the money because the government's going to take it from you. So helpful people will say, oh, okay, you just won, you know, $5,000. I'll give you $2,500 for the ticket, or if they're really mean, that's like, okay, here's $1,000 for a ticket, and they take the money. All right. So, well, anyway. So let's talk about a little bit about gerrymandering. So I'm from North Carolina, so this is sort of an issue, you know. Half the state is Democrat, half is Republican, but for some reason, in Congress, there are 10 Republicans and 3 Democrats. So how do you do this? Well, you suppose you have 200 times N Democrats and 200 times N Republicans. You make 3 districts that are 60-40, Republicans versus Democrats. And then you have one Democrat that's 20-80. One district is 20-80. So the Republicans are pretty sure winning 3 districts. And the Democrats, District 4 is like Durham, you know, but it wasn't designed like that. So, and that's for 3 districts out of 4. If you take 13 districts and you do this cleverly, then in the 2016 election, 10 Republicans won and 3 Democrats, even though the thing's roughly 50-50. All right, so had an interesting discussion over lunch yesterday. Whether is this illegal, I don't know. It's not fair, but you know. All right. So let's show you the shapes of districts in North Carolina. All right. They sort of look funny. There's, I don't think I've pointed. Well, but fortunately, the purple one shows up pretty well. All right. At the bottom of the purple thing is Charlotte. Right there. Now, the purple district goes up along I-40 because lots of people live on the interstate, you know. And at the top, it gets to Greensboro, which is another big town. And then it goes up to Winston-Salem. And I hadn't been in North Carolina long enough to know what's there. But it's a very, very tiny district in terms of area. And it's about 80% Democrat, 20% Republican. You know, all these things are not so bad, although the orange one is it sort of looks like Vietnam. You know, it's just stuck somehow inside the red one. You know, it looks like a sort of jigsaw puzzle. It's like they didn't want the dark blue district and the light blue district to pull apart, so they put these little things in there. So this is, and this other thing, I got a minute. Whoa, no. This thing out here looked like, oh, well, what's wrong with the end of North Carolina? This is something called the Outer Banks. There's a sandbar, and then inside it is, you know, inland sea. And there's it's hard to get to what's on the sandbar, but it's a really nice place to go to the beach, you know, so that's not part of gerrymandering. They didn't make this big lake, you know, for that. All right, so the districts look weird, but does that prove anything? No. I mean, it's just maybe they had a little too much wine when they started drawing the map, and they started saying, oh, that looks cool, you know, so. All right, so you can ask yourself, what would happen if we drew districts at random? I mean, this is something you would think about in statistics, you know, so. So what would districts look like if we were drawn at random? Now, if you take all the people in North Carolina and assign them at random to 13 different districts, that would look like a mess, right? So the districts should be connected and compact. If you're taking analysis, I'm not talking about that. I mean, sort of, the district is closed and bounded, so it's going to be compact, you know. So, and it should minimize the splitting of counties, right? So Jonathan Mattingly, who's my chair, so I have to mention him in my talk, you know. So, he's been working with undergrads, grad students, and postdocs for about the last 4 or 5 years to develop methods for randomly sampling from possible redistricting plans. All right, so this is not something I really want to go into. They have ways of sort of, I guess they move things around at the precinct level. They propose a move, look at how good the district is, decide to accept it or not, you know, so. And in an analysis, they generate about 24,000 of these and retally the votes. So he's done this a lot. 2012 election, the thing is a little confusing. I mean, there were different maps used in 2012, 2016. So the thing really to look at is sort of the orange bar that in 2012, 4 Democrats won, and this histogram tells you what should have happened with randomly drawn districts. And then 2016, some guy named Trump won the state, so there were fewer Democratic votes and, you know, only 3 people. But then, you know, there's this histogram. I don't really know anything about statistics, but this looks like it's not a typical draw from the distribution. In fact, that if you redistricted at random, only 1% of the time would you get something like this. All right, so unfortunately in statistics, this doesn't mean that, we have to redraw the district lines. You know, it was moving up through the courts, and then it didn't get all the way to the Supreme Court before the time for declaring for the primaries was open, so this whole thing's on hold for a bit. All right, so, well, better to be too short than too long, I guess. The gerrymandering stuff, they've done for not only for North Carolina, but also for Pennsylvania and Wisconsin. Nobody's going to write down the URL, but just sort of like you guys know how to use Google better than I do. You can probably find that. And all the slides, in case you want to amaze your friends, tell your mother some interesting facts about what you've been learning at college, they're on my webpage, you know, so. And, okay, well, I'm done. Well, I was just sort of quoting from the paper, and I did this sort of quickly. I mean, when the North Carolina legislature wrote down what properties do we want our districts to have, right? It doesn't do such a bad job of, look at the dark blue versus the other blue thing. Those things are pretty, well separated. I mean, some of them, are entwined inside the other one, but, most of them are connected. They have sort of strange shapes. But, I'm not saying the Republicans followed their own rules, but, if you went and started adding and subtracting precincts without doing something to this, then you'd have districts that were like snow across the thing. So they use this, in a sense, to make realistic-looking districts. I mean, if you look at the... I didn't quote this. There's a paper on the archive that talks about how it's done in detail. But, they've been developing the methodology for 4 or 5 years. They want to develop realistic districts, and yeah, I mean, these things are maybe if they ran their algorithm, they wouldn't generate anything like this. But, you have to do something to control for the shapes. Other questions? Okay. Darn, I was going to have them take out a piece of paper and number 1 to 10, so. Okay.